Hi, student. Now we will continue on the energy balance. Previously, we talked about the energy balance based on the heat change due to the temperature change, which is constant due to the temperature change, due to the temperature constant, or temperature change due to the volume change that we talk about the CV, Cp. Now we consider based on the phase change, the entropy that involved for the. What do we talk about the latent heat? Latent heat, there is the entity of phase change. It is specific how we change associated with the transition of a substance from one phase to another phase at constant temperature pressure. That's why what we talk about the heat of fusion or heat of melting. Heat of fusion we talk about is the difference between solid and liquid. It's constant T and P constant temperature and pressure. Uh, Fusion is solid to right? Fusion is solid to liquid. Melting is I'm so sorry. Is fusion is liquid to solid. Melting is solid to liquid. Like the switching and also heat of vaporization. Vaporization from liquid to vapor or to gas, and condensation is gas or vapor to. And also we talk about the delta SM, fusion or melting, delta SV, vaporization or condensation. This also occur as constant pressure and temperature. Or the first case we talk about the heat of vaporization. What less in kilowatt must heat be transferred to a liquid state from methanol at its normally point to generate 1,500 grams per minute of saturated vapor. For this case, we can calculate enthalpy of vaporization and boiling point of methanol. We can open from table B. I will open from the book. Methanol. Also, you can use the database on online database. Case for this mostly found in table B1 in this book. Okay, table B1, we talk about the formula, the chemical species, the formula, molecular weight, Hg. They talk about the density, melting point, delta S of melting, boiling point, delta S, delta V, delta SV of evaporation. The right for this, the column is kilojoule per mole delta SV, boiling point in delta C. Talk about the methanol. That's right. Methanol or methyl alcohol or methanol is the melting boiling point is 64.7 and heat of vaporization is 33.27. It is from the table B1. You get data SV is 35.3 kilojoule per mole at boiling point of 64.7. That is energy balance for there is no kinetic energy, there is no potential energy, and there is no work. You get Q equal to delta S. Delta S equal to mole multiplied by delta SV. That's delta SV in terms of specific enthalpy. That's right. Kilojoule per mole. Multiplied by number of mole, you get kilojoule. And N in terms of mass. That's right. Okay, we get this 1,500 gram methanol per minute, and then you change from gram to mole. You divide this by molecular weight. 32 gram methanol equal to 1 mole. That's right. Multiplied by delta S V is 35.3 kilojoule per mole. Right? Mole is cancelled. Gram is cancelled. And then you change from minute to second. 1 minute equal to this second. Right. This is the kilojoule per second. You know, right? 1 kilojoule per second is 27.6 kilo. Yes. And for the second example, we talk about the vaporization and heating. 100 gram mole per hour of the liquid hexane at 25 Celsius, 7 bar is vaporized and heat to 300 Celsius as constant pressure. Have two steps. In hexane heat from 25 to the boiling point, and then at vaporization, vapor phase also heat to 300 degrees at constant pressure at 7 bar. Right. For this case, if we neglect effect of pressure on enthalpy, what is the rate at which heat must be supplied? Must be supplied but heat add to the system. For this case, if we have no the work Cp and we have no the kinetic energy, that's right, Q equal to the S for open system. But for this case, we only determine delta S. Delta S involved in the heating, involved in the phase change. Have to get that's right. Okay. The first step we have to know what is the boiling temperature or vapor pressure. That's right. The first step we can look at this hexane. That's right. What is the boiling point of hexane at 7 bar? At 7 bar, that's right, is we get about this. In hexane, right? Yes. Okay, is around like 146, 46 degrees Celsius is the boiling point at 7 bar. That means the in hexane will vaporize at 146 at 7 bar. And also if you pen table B1, this is the boiling point at 7 bar. And also you can open B1. The B1 is the boiling point at approximately 1 bar or 180. And to in hexane, that's right. In hexane, that's right. The boiling point is approximately this 0.74, that's right. That's indicate the data SV is 28.85, approximately 69 Celsius, and data SV is 28.85. This is from the table B1. Okay, we can use case for calculate data S, but we have some reference to state. For this case, you have to draw the diagram. In that case, we would like to change the N-hexane liquid to N-hexane vapor at 100 degrees Celsius at 7 bar. We have two steps. From the first step, we change N-hexane 20 degrees Celsius 7 bar to vapor at 7 bar. But we don't know this data. And vapor at 25 degrees Celsius to 200 for the EF state. For this case, we have know the data of entropy for this, right? And for this case, we can calculate by Cp. We have know this data. We have to another part. For that case, we change the at 25 degrees Celsius to 96 Celsius. This is the normal boiling point. And also you have to decrease pressure from 7 bar to 1 bar, approximately 180. They have two steps like this. From 25 to 25 at 7 bar or 7 atm approximately. And then you change the sorry, this is from 25 to 69. That's right. 25 to 69 first and 7 bar. And then you change the sorry, this is okay. First step, you have to change the pressure, that's like 20 degrees Celsius, 7 bar to 1 bar or 1 atm, and then you change the temperature from 25 to 69. For this case, we incorporate in the CP, that's right. Incorporate the CP. The first step is the pressure change. For liquid phase, the pressure change is equal to 0. That's right. The U equal to 0. Yes. The U equal to 0. Okay. And then you can change from 69 to 146. It is about boiling point at 7 bar. And then evaporation. And then you decrease temperature 300. Increase temperature to 300. You can follow this part, or you can follow this part. This part you can boiling point evaporation of normal at 69 degrees Celsius 1 atm to vapor phase at 69 Celsius 1 atm. Then you increase the temperature and increase pressure. And also for this case, you can have two steps. That's right. First step, increase pressure at constant temperature. That is the V delta P. For this case, from the step G, we have two. That's right. We increase the pressure from 1 bar to 7 bar first at constant temperature. For this case, ideal gas, we get delta U equal to 0, delta S equal to V delta P. And then for this case, from constant pressure and increased temperature is Cp. For part A, we have two steps. We decrease the pressure from 7 bar to 1 bar or approximately 1 atm at 25 degrees. For this constant pressure, constant temperature, change in pressure, but for liquid phase is equal to 0 delta S, delta U. Okay, but for this system, we will follow this ADG system. ADG system. For this case, we follow like 25 degrees Celsius, 7 bar to 69 degrees Celsius, 1 atm, and then 69 degrees Celsius from vapor at constant temperature and pressure, and then from 69 Celsius, 1 atm to vapor, that's at 300 Celsius, 7 bar. For this case, I talked you already. Delta SC include like the V delta P for constant temperature change pressure. Delta SA include like the constant temperature change in pressure. But for this case, the constant temperature change in pressure, delta S equal to delta U equal to 0 for the liquid phase. That's right. And then you have to calculate delta SA, delta SD, delta SG. Delta SA, that's right. For this, we have two steps, right? For delta SA, this includes the temperature change from 7 bar to 1 bar as constant temperature. Right? For liquid or solid phase, delta SU equal to 0, and then delta S equal to V delta P. And then also integrate dP dt for 25 degrees Celsius to 69 degrees Celsius. Like 2, yes? Yes. V delta P. Indicate Cp dt from 25 to 69 degrees Celsius. And the second step is from liquid at 69 degrees Celsius to vapor at 69 degrees Celsius constant pressure related to the rate of vaporization. Okay? And the third step, G, delta Sg. For delta Sg, this includes the constant temperature change from 1 atm to 7 atm. But for this case, V delta P equal to 0 for ideal. That means delta U equal to 0. There is something wrong. In this case, delta U equal to delta S equal to 0 for, as I assume we ideal. And also plot the indicate Cp dt from 69 to 300 degrees. This the second step. SA includes 2, right? Sg includes 2 also. But SA in liquid phase. The first is the pressure change. The pressure change delta U equal to 0, and then delta equal to V delta P. In this case, vapor phase, the pressure change is approximately 0 for delta U and delta S. That means V delta P equal to 0. For this case, we have only term of Cp. Okay. From this case, we have to calculate V delta P. That's right, the volume is 1 liter per 0.659 kilogram. This is the density. That's right, it's the density of exhaust multiplied by delta P. That's right, this decrease from 7 to 1.013 bar. Okay, we get this. and multiply by the molecular weight of n hexane. Then you change the unit, right, from 0.0038314 kilojoule per mole Kelvin, also equal to 0.08314 lit bar per mole Kelvin. And this is the first term based on the pressure change and temperature constant for liquid phase. Delta U equal to 0, and then delta S equal to 0 plus V delta P. And the second term, that is due to the temperature change from 25 to 69, right? 25 to 69. You integrate Cp, or the Cp of n hexane is constant. In this case, you substitute Cp in constant, and then you integrate. Right? You integrate Cp. Get this? And then you get two terms, and is it 9.44 kilojoule per mole. This is delta Sa. And the second term, delta Sv. Right? The part D is delta Sv. The Sv is 28.85 kilojoule per kilogram. Okay. The third step, delta Hg. Delta Hg include like the pressure change from 1 to 7, but for this case it's ideal gas. We assume ideal gas. Delta U, delta S equal to V delta P equals to. Okay, this equal to 0. It's only the term, right? Temperature change from 69 to 300 degrees Celsius. Right? But for this case, Cp of hexane in vapor phase expressed in this equation. Right? Cp of vapor phase is changed with temperature, but Cp of liquid phase is constant. For that case, you substitute Cp for this, and then you integration, you get delta Hg equal to 47.1 kilojoule per mole. Right? Kilojoule per mole, and then you multiply, and then you summation delta S. Right? Delta S equal to Sa, Sd, Hg. Sa equal to this, right? Hg equal to this, and Hg equal to this, and Sd equal to this. But Sd you have to change, right, the unit from kilogram per kilojoule, right, to kilojoule per kilogram to kilojoule per mole. That means you have to multiply by molecular weight, right? Multiply molecular weight. And then you get Q equal to delta S equal to 5.5 kilojoule. And then you calculate Q in terms of energy, rate of energy. For this case, we have 100 mole per hour of NX. You multiply 100 mole per hour. Let's multiply by Q. And then you check the convert unit from hour to second. So mole cancel. It kilojoule per second. You know 1 kilojoule per second is 1 kilo. At 2.8 kilowatt. And then you get the Q. But for this case, there are some comment because the pressure change in the first step is approximately 0.07 2 kilojoule, but it's very, very small value. For this case, I assume, right, you can cancel this, but it's very, very small value. But don't worry about that. And include or not include. And then how to estimate if you have no the data of latent heat of fetching, latent heat of melting, latent heat of evaporation. Have some estimation correlation equation. By the first equation, like we try to chosen do a simple formula for a standard heat of vaporization at normal boiling point. Delta SV equal to 0.088 TB. It is for non-polar liquid. This is at normal boiling point at 1 atm. And also equal to 0.109 TB. This is for water or low molecular weight alcohol. Like TB is the normal boiling point. But for this rule is the accuracy within 20%. And another question is chain equation. This is 2% accuracy than the Newton rule. The formula is the delta SV we can calculate from the TB multiplied by 0.0331 TB divided by TC minus 0.0327 plus 0.0297 log PC divided by 1.07 divided minus TB divided TC. TC is the critical temperature. B is boiling point. And also you can evaporate on the Clausius-Clapeyron equation, which is log is vapor pressure equal to minus delta SV divided by RT. If you know B, you know P star, you know T, you can calculate delta SV. This is the information from Crousset-Carbillon that so we have the data in the literature already. Is from the experimental data. And also if we can approximate the entropy of another temperature, Watson correlation, a useful approximation for estimating latent heat of vaporization at T2 from a known value of T1. If you know the entropy of vaporization for the temperature, you can estimate for outer temperature. This is expressed in delta SV at T2 equal delta SV at T1 multiplied by the ratio of TE minus T2 divided by TE minus T2 of this power 0.38 with the TC, that's like this TC, with the critical temperature. And also for the formula for approximating the standard heat of fusion, you can calculate the rate of fusion of liquid to solid by delta Sm equal to 0.0092 Tm. This for metallic element and also 0.0025 Tm is inorganic compound. Also 0.05 Tm is for organic. You can use to estimate the delta SV if you have know the information in table, information in literature. You can use this equation to estimate like delta SV, Sm. Yes. Like for example, right, we have the normal melting point of methanol is 337.9 Kelvin, and you know the critical temperature of the substance is about 513.2 Kelvin. Please estimate the heat of vaporization at 200 degrees Celsius. In this case, the first step you have to estimate the delta SV at 300. That's right, 337.9 Kelvin first, and then you use the estimated between temperature. Okay, the first step for this case we use like the Charlton rule. That's right. For methanol is the low molecular weight alcohol, and use this formula for Charlton. Delta SV is approximately equal to 0.109 TB. You know TB. You know TB. You can calculate 36.8 kilojoule per mole. This is approximately is close to the value from the table. That's like this measurement value. And then if you use the chain equation, delta SV equal to this term, approximately 37.2 kilojoule per mole. That means the total load is close to the true value. And then you can calculate at another temperature by the Watson correlation. That means delta SV at T2 equal to delta SV at T1 equal to the Tc minus T2 divided by Tc minus T1 over 0.38. For this case, T1 is 337.9, T2 is 473 Kelvin. Then you can calculate like the delta SV at 473 Kelvin at 20 joule per mole. This is how to estimate if you don't know the information. For this case, the total rule is accuracy than like the chain rule or methanol. Okay, for the next example, we will show you how to use the heat of vaporization, heat of fusion, or latent heat of phase change, sensible heat, or specific capacity of the system that change in temperature, or delta U, delta S based on change in pressure to incorporate in the energy balance. Example, okay, for this case, we consider the partial vaporization of a mixture. The feed we contain a mixture of benzene and toluene at equimolar mixture. That means 50% mole of benzene mixed with 50% mole of toluene. It feeds continually to a wet cell, right? In which the mixture is heated from 250 degrees Celsius. The first step, we have the mixture of benzene and toluene at 10 degrees Celsius. Sent to evaporator. The temperature is heated to 50 degrees Celsius. For partial, the liquid product is 50% more benzene, and the water product is 68.4 mole benzene. That means some parts of benzene content, some part of toluene content. And for this example, we know right the component in vapor phase and liquid phase. We have two components. We know benzene, and then you can calculate. And the question is how much heat must be transferred to the mixture per gram mole of feed. Per gram mole of feed, that means you can add to feed it 1 mole. Per gram mole, that means feed it per gram mole. And then you can base it based on 1 mole of feed. Okay. For this case, we know 1 mole of feed, and you know composition of feed. You know temperature of feed. And the product after evaporation, we have two in vapor phase and liquid phase. You know composition in vapor phase. Right? It's 40%, 68.4% benzene. And in order you can balance that 0.684 mole benzene, 1 minus 0.68 mole equal to 0.316 mole of 2. Also, you know the product liquid is 40% mole benzene, that is 0.4 mole benzene per mole total. And then you can calculate 1 minus 0.4, you get 0.6 up to the. For the output in vapor and liquid in saturation, that's is 50%, 50 degrees Celsius, also 50 degrees Celsius. Then you can open and you get the pressure. And then you denote NV is the mole of vapor, NL the mole of liquid phase. And also we have calculate Q. For this case, we assume right there is no kinetic energy, there is no potential energy, and there is no work. That's right. Q equal to delta S. This open system have flow in and flow out. If we consider the degree of freedom analysis, we have three unknowns, NV and LQ. We have two material balance, that's right, toluene, benzene, or total mass balance. But we have three species, but we have only two independent equations. And we have one energy balance. Okay, this zero degree of freedom. You can solve that. First step, you have to make a material balance. You can make total mass balance, benzene balance, or toluene balance. Right. For this case, we make like the total mass balance first. Total mass balance, feed is 1 mole. And output is NV plus NA. There is no generation, there is no consumption. And there is no accumulation because we feed in and flow out continuously. N 1 mole equal to NV plus NA. And the second balance for this case, we use the benzene balance. How much benzene input? Benzene input is 0.5 multiplied. Benzene output equal to 0.684 multiplied NV plus 0.4 multiplied by NA. There is no generation, no consumption, no accumulation for benzene. And then we have two equations and two unknown. You can solve simultaneously. You get NA equal to 0.35. NV equal to 0.352 and NL equal to 0.64 S mole. And you know NV, you know NL. And now we have only one unknown is Q. Q equal to delta S. For this step, you have to contact the table of energy. That's right. We have two components, benzene and toluene. We have two phase, benzene liquid phase, toluene liquid phase, benzene vapor phase, and benzene toluene vapor phase. Okay, for this case, mostly we have know the table of benzene and toluene. We have know the table of entropy for this case. For this case, we have choose one system as the reference. But mostly we should like the liquid phase as the reference. Okay, for this case, we choose the liquid feed as the reference state for both benzene. That means benzene feed at 1 atm and 10 degrees Celsius as the reference for benzene. Toluene liquid phase at 10 degrees Celsius and 1 atm as the reference for toluene. That means entropy of input of liquid benzene and toluene equal to 0 because it's the reference. And the column, this is show the mole of benzene and toluene. Okay. Right. Now about the second column of benzene vapor and toluene vapor. There is no benzene vapor and toluene vapor in the feed. Okay, there is no feed. The second and the third column, okay, we consider already. And the fourth and fifth column. The fourth and fifth column we consider about the mole and entropy of output stream. The output stream we have four components. We have pure phase of benzene, pure phase of toluene, liquid phase of benzene, liquid phase of toluene. For this case, is at 50 degrees Celsius, right? And 44.8 millimeter. In this case, you have to evaluate S1, S2, S3, S4. S1 is benzene, entropy of benzene output. 2 is the energy incorporated is toluene, liquid phase output. 3 is the energy associated with the benzene vapor output. S4 is the energy associated with the toluene vapor output. In the first step, for this case, you have to evaluate the S1, S2, S3, S4. S1, the energy at 50 degrees Celsius, reference to 10 degrees Celsius liquid phase from vapor at 50 to liquid at yes. Okay. For S1, S1 we change the liquid phase from the toluene from benzene at 10 degrees Celsius liquid phase to the benzene vapor at 50 degrees Celsius. Okay. In this case, we for S1. S1 is okay liquid, only liquid. There is no phase change. S1 is change from 10 degrees Celsius liquid phase to 50 degrees Celsius liquid phase. The temperature from NSM to 34.8 millimeter mercury, but the temperature is changed a little bit. For the liquid phase, we assume that the energy due to the pressure change is really small value. Give an example, we can answer. In this case, there are only the temperature change. That means Cp dt. You get Cp dt. In this case, you have to open for the Cp dt from table B2 of benzene. Then you substitute and then you integration from 10 to 50, you get this value. Get this value. And also S2 is the toluene liquid phase from 10 to 50 degrees Celsius. In this case, the temperature constant and pressure change a little bit. Okay, the first term is 0. You did not consider like the pressure change, and we only consider the temperature change. That means we only consider the term integrate Cp dt. Find the Cp equation from table B2 and integration from 10 to 50, you get the result is 6.434 kilojoule. Okay, and then we consider S3. So we have three steps. It's the vapor benzene at 30 degrees Celsius. This step, the benzene liquid phase at 10 degrees Celsius to benzene liquid phase at 50 degrees Celsius. Okay. Second step, benzene 50 degrees Celsius liquid phase to benzene 50 degrees Celsius vapor phase. And the last step, yes, they change to the the change from right. We have three steps. Benzene liquid phase to the boiling point, right? To the boiling point. First, the boiling point of benzene is 80.1 degrees Celsius. 80.1 degrees Celsius, and then you decrease the temperature from 80.1 to 50. And also for toluene, we change to the boiling point at 110.62 Celsius. Okay, this is the change in temperature from 10 to 110.2 Celsius. This is the change phase, that's right, at constant pressure and temperature. And this is change in temperature, that's right, change in temperature from 110.62 Celsius to 50. Okay. For this S3 and S2, right, the change in pressure is negligible. Aside from previous example, we can conclude that the change in pressure is very small value of the entropy. We can neglect that. For this case, also the first step we change pressure also. That's right. Pressure also from 1 atm to 34 millimeter mercury, something like that. It's not. And also did we change the pressure also. Pressure change is not included in it. It's at 3 and at 4. Okay. We only consider the change in temperature and where change in phase. Then finally you calculate right the Q equal to delta S with delta S equal to summation Ni Si minus summation Ni Si of input, output and input. This case get right. Output is 0.259 multiplied S1 plus 0.3989 S2 plus 0.241 S3 plus 0.111 S4 minus 0. For input is 0. And then you get like 17.70. This case for when you do the enthalpy balance, that case you change the temperature. You change the temperature, you change the pressure. Mostly when the term of entropy incorporate or associate with the change in pressure is very small value compared to the other. Like this example, right, I show you in the comment. This case we change for the pressure for the liquid phase is V delta P, but V delta P we look at the value is about 0.0782. It compared to another one is very small, but you can cancel for the change in pressure. You can include or not, don't worry about it. Value is very small. Small value in error when you pressure. For the example, we have right the two step also for this case S1. That's right. S1 there is no. Is also right the pressure change. That's right. S1 is liquid. S1 10 to 50, but we change pressure from 1 atm to 34.8 millimeter mercury also. You have to change, but the pressure change is very small value. You can make that. Yes. And S2 also we change the pressure change. S3 we have the change pressure in this term. And in change in this pressure, but the change in pressure is very small value. You make it. And then you get only the temperature change. That's right. Get this way. We stop for the time. We continue later. Energy balance based on non-reactive. You